Hey everybody, this is Larry. This is day 24th of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. For a second, I was like, I have to wait for this to load to tell me what day. And I was like, oh wait, I don't need to do that. Just intuitively, or intuitively? Huh. No, just regularly press that button anyway. Anyway, yeah, how's everyone doing? We have a hard problem today, so I look forward to spending a good amount of time together. Today I ran 5 miles, easy 5 miles. Unfortunately on the treadmill because I don't know, just the timing goes. But as a result, I don't know. We'll see. I took a nap actually afterwards, and I just woke up, so maybe that the nap was refreshing. The workout, I'm just not in shape for. The marathon's gonna be a pain, but you know, it is what I signed up for. Anyway, yeah, let's take a look at this one. Yeah, let's take a look. Let's get to it. All right, 22. Minimum score after removals on a tree. There's an undirected connected tree of n nodes. Okay, it's just a tree, right? N minus one edges is a tree. Assuming that's connected. You're given a zero index integer array nums of length n, where nums of I represent the value of the ith node. Okay, so you know, I don't know what the number. Oh, okay. So the blue has edges, or blues are the values. Okay, and then you have edges that indicates number. Oh yeah, you have edges, which is an edgeless, right? Or adjacency? No, an edgeless. Remove two distinct edges of the tree to reconnect the components. Okay, so basically you removed two edges to have three trees. So one tree in the three tree, and you have a little bit of a forest, even though it's a very small forest. Alright, anyway, alright. For a pair of the removed tree, get the XOR of all the values of the nodes in each of the three components. The difference between the largest XOR and the smallest XOR is the score of the pair. So example, okay, with the minimum score. So the minimum score means that the largest and the smallest score has this as close a score as possible, right? Okay. And I assume that, actually n is 1,000. I was going to say, I assume n is like 10 to the 5th. Otherwise, maybe it's not that interesting. N to 1,000 is interesting in that the n minus 1 edges, right? And because the n minus 1 edges, if you iterate, if you want to remove a pair of edges, it's going to be n squared, right? Where n is the number of nodes and also the number of edges. So that means that you can enumerate removing every pair of any pair of trees, any pair of edges which creates this, right? The question is then now, okay, let's say you have an n squared algorithm. What does that mean? That means that if you're able to do every pair of edges, you have to be able to do the calculation in all of one, right? Of the 3 XOR values in all of one. Because if you have the 3 XOR values, then it becomes pretty straightforward. Well, I mean, the rest is just, if you have the 3 XOR values, then you just have to find the difference to the largest and smallest. That part is easy, assuming you have the 3 of them, right? So then now the way to kind of boil this down is that, okay, so maybe we have something like for every 2 edges, or every pair of edges, maybe a pair of edges, calculate the 3 XOR values, right? Okay, so then how do I think about this? So okay, I mean the thing about XOR, there's some properties that you have to think about, right? And I'm bringing up the drawing board. Hang on. I mean, I have an idea, but I don't know that I have everything all together yet, because I want to explore it with you, right? And you know, okay, yeah. So the idea about the observation or the thing you have to know or figure out or whatever about XOR is that okay, that's terrible. All right. Instead of drawing coloring in, I'll just So you know you have nodes, right? And the first thing that you can do is just get the XOR of the entire tree of every value, right? So let's say you have some value X. And then what happens, what does it mean when you remove, or when you have like 3 sets of nodes, right? So maybe say you remove, I don't know, this one and say this one, right? What does that mean? What that means is that then now, let's just call it this chunk A, this chunk B, and then the rest is going to be C, right? So then now, A XOR B XOR C is equal to X. And that's all you have for this, all you need for this one, right? Is that given X, you know X because we calculated or whatever. If we are able to figure out A and B, then we can figure out C, and then we could just do the math of finding the min between the largest and the smallest, or the delta between the extremes or whatever, right? And then for me, my idea then now, I'm still trying to figure out how to brute force, to be frank. And what I mean by that is that, okay, well, here, I mean, one example is what we drew here, right? It's just 2 subtrees, right? 2 subtrees, that's an easy, we could just calculate the values of all the subtrees, and 2 of them that don't intersect, right? And then, so this is one case, and then the other case is if the, let me redraw this. All right, well, I hope you took a note of this because I'm deleting the entire thing. But so let me write it out, right? So you have 2 cases where, you know, some subtree. This is supposed to mean like a lot of nodes, and then you have like 2 subtrees, right? And then the other case, of course, is if one is the subtree of the other. So then you have like right? I don't know, something like that. And then you want to say this subtree, this subtree, and maybe this subtree, right? So you have like this, and also in another color, this, right? And you can do the math for this as well, right? And what I mean by that is that, you know, you have some value X for the entire tree, and again, it's still going to be true that, well, maybe not like that. Hang on, right? You know that, let's say you have A, B, C, you know that B XOR C is equal to X, and then you have, you know that A XOR, oh sorry, I guess maybe my B is not clear, but you just have to draw it out kind of thing, right? Because B, let's say B is the entire red thing, and then this thing, maybe that's a little bit confusing. Maybe this is BT for B total. Whatever, let's just call this D, the green part D. Then now you have A XOR D is equal to B, right? Again, yeah. And that's basic, and I mean, with this formula, that's all you need, right? And of course, if you kind of substitute, it's still the same, right? Because now you have 3 sets of nodes, so A mod D, XOR, sorry, XOR C is still equal to X, just that, you know, just that if you get the B part, you know, A XOR D is equal to B, right? Okay. That's basically, I mean, everything I've said so far, I figured out on the fly, right? Like I didn't, I mean, I think those are the 2 cases because, you know, without loss of channel, just give me, you know, but yeah, you can figure this out by just drawing diagrams. That's basically how I would like to think about it. Okay, so now we have these 2 cases, and then what do those 2 cases mean? Well, I think stepping back a second, what does it mean, right? So I say things in terms of subtree, and the reason why I want to say that is because then now for every node, instead of removing edges, you could say maybe I want to say for every node we remove the parent edge, right? The edge that goes back to the parent in a rooted tree. I mean, you can root it in any way you want. I don't think it matters that much, because yeah. But once you root it and you have a direction, then now you just want to remove the edge to the parent, right? And then now you could say this is this subtree, and then now you say the same thing for the other one, and then basically what you're now iterating, instead of two edges, you want to iterate two kind of roots, right? Roots of the new tree, if you will. And then now, then how do you differentiate between this case here where they don't, you could say intersect maybe, where they don't intersect each other, and here where, well, the intersection is kind of terrible word, because if it's a subtree and that's the identical, it's either it's going to be a subtree or not a subtree, right? Meaning that you have A and B, either A is in B, or either one is in either one is in and the other, or they're not, right? So you have this case where they're not inside each other, and then you have the case here where they are, right? And then the question is, well, how do we differentiate between them? And here, it should be pretty straightforward. I don't know if it is, honestly. But it's straightforward to me in terms of just literature, right? And what that means is that, well, even looking generically, let's just say you want to look at this node and then some children other node, right? And you just have to you have to pre-process the tree in some way. I'm hand wavy here, but we'll go with some parts of it because some part of this is literature. And by literature, I just mean like, you read up on a book or YouTube or something. But the question is that you just kind of, it's pretty straight. It's not even, I was going to say LCA, and you can't do LCA standing for least common ancestor. Right, so you could do that. You can also just check whether one is inside the other, right? So you make an is call, right, where is the ancestor, and that's it, really, right? So you just make an ancestor call. I was gonna say that you could do something funky. No, it's not that funky. It's just literature with like what's it called? Binary lifting or something like that, or either binary lifting or repeat doubling and stuff like that. But actually, they're all, n is only 1,000, right? So you can actually pre-calculate all of this, right? Because there's just only n square pairings to pre-calculate, so that should be fine too. Yeah. So we can definitely do, there are a lot of stuff we can do, but you can pre-calculate its ancestor core, and then now we have everything we need, right? Because now what we want to do is just we want to calculate the value for, so in terms of looking at edges, we look at nodes, as we said, and when we look at nodes, we just look at the, let's just say we call it the subtree XOR value, right? And that's it. And we calculate for every node, and then you have the two cases, and we are Gucci. So let's go. I think we have enough to implement, and everything's going to be n squared. So yeah. Sorry if I'm like pausing a lot, because what you watch is not me like this. Because sometimes I do jump straight to the answer like in my head, and then I explain it slowly again. But for this one, I am actually like working out the cases in my head. And as a result, you are seeing this live of me figuring this problem out. I mean, a little bit, obviously a little bit slower than I would be if I wasn't, explaining, but overall not too bad. I don't know how this took like 14 minutes. I feel like I feel like that was pretty okay, but maybe I'm just explaining slowly. Okay, in any case, yeah, so then now we want to say, there are a couple of things we can do first, but let's just say pre-calculate is ancestor cache or whatever. So n is equal to the length of nums, and then so then we can do that by just with well, we have to convert it to adjacency list first. These zero, nope, zero index. Just I always mess that up, so I want to make sure. And then we can pre-calculate by just doing as part of a depth first search. As I want to, you can do it in any number of ways though. You could maybe say, naming things is hard. I'm just I just go depth first search then with the current node, and then maybe ancestors. Right. Let's also have just the parent, just for easier to do it, right? So then now we can say for A in ancestors. Oh, I have to do a map. So maybe we have like a. I guess this is actually not Pythonic, but so something like this, right? And you can maybe say like a node should be its own ancestor, maybe. I don't know. Maybe it's not that interesting. We can figure it out later. We want to just say in ancestors of so node A is equal to true. Nope, the other way around maybe. And yeah, the ordering doesn't matter. You just have to be clear, right? So in ancestor of AB is equal to is A an ancestor of B, right? And then now for B in adjacency list of node, if V is not equal to parent, then we just go TFS V node okay. Dot append not V, we want to append node. Something like this, right? And then we just want to start from any node is fine, so 0 is good. And then yeah, and then maybe a node of no, just empty node is fine. Right? And then now we should after we pre-process this, or after this it pre-calculates in its ancestor, right? Now we can probably actually do stuff on part of this, but I'm going to separate it out in two depth first search to kind of just like have a modular way of thinking about it. But I wouldn't be surprised if you can just do it as part of this, right? So maybe we'll use a terribly named DFS2. You have node parent, and then maybe the current xSum, right? XOR sum. And this is structurally very similar for, well, I mean, it is just another depth first search. And then maybe we have keep track of sums. xSums is equal to 0 times n, or maybe just go in none times n. I like to go in none because if it shows up as none at the end, that means that something went wonky and you didn't process all the edge or something, versus like a default sentinel value, which is fine, but it hides your error during testing, possibly, right? Anyway, yeah, so then now this is the same as before. You have V node. We'll figure out how we're going to do it. I mean, we know this is known. I forgot to do this, but I just haven't gotten to it. Okay, so this is roughly right. We want to say XS. Oh no, we want to say okay, yeah, current. We want the current is equal to we want to store XX of I is equal to the subtree XOR sum at node I, right? So then current, we want to contain the current node. What is it called? Nums sub node. And then we want to include all the nodes that are in the tree, and then that's it. And then we want to return current, but we also want to save it down at the end, and that should be good, right? Because you have to do it again from right? Okay, I'm gonna run it real quick. It doesn't show anything. I just want to see if it crashes, right? Like I don't know, if we have something that goes out of bounds or something like that, then I'll look at it now. Right? But I mean, I would say I'm relatively confident, but a lot of things goes wrong. Just typo. I'm getting old, right? Okay. So now we have DFS, DFS2. We have the two nodes, or we have the two things processed, and then now, yeah, try every pair of nodes, right, as the subtree, right? Oh yeah. Oh, I guess I was gonna say I forgot to check the one with the entire tree, but then yeah, that's just actually rooted at the the root, right? So we can just do that. Yeah, right. So total, maybe you could say, is equal to excess of 0. And I'm just going through the case where do you iterate on the root node? And I want to say the answer is probably not, because if you have one of the nodes as the root node, that means that you only have two components, right? So that means that the root node has to be one of the things that you don't exclude, right? Because if you just think about it, if you have like and we had it in ABC form, right? But if you have node A or B as the root, then what happens? If that's the case, then if A is the root or B is the root, then what happens is that, well, what happens is that you don't have room for C, right? Or if you do and A is, then it just becomes another case that you already considered, I suppose. Okay, so then now we have maybe for A in range from 1 to n, because we're rooted at you know, and here we maybe just do this because there's no loss of generality, right? Because if you just flip them, then they become the same. So I think this is fine. And then now yeah, so then we have two cases. I want to say if maybe I guess it matters, because in the sense of, okay, maybe I'm wrong on that right now, but that's fine. I mean, whatever, we'll write it out. So if is ancestor, no, I think in this way is a little bit cleaner, because then now you do the disjoint set a little bit differently. So okay, if A is ancestor of B, no, I can't do it that way. Whoops. No. Okay, fine. I guess I have to do it this way. It's just about handling the cases. There's nothing you have to think through it. That's basically what I'm doing, right? Is A ancestor of B? If A is ancestor of B, then and honestly, if I usually I would write my notebook and then I would refer to my notebook of what happens, because I have different cases. I already drew it out, and I'll be like, oh, A is ancestor of B. That means, you know, right? But this time is a little bit trickier. Because I deleted the art even on my paint thing. So, okay. So A is ancestor of B. A is ancestor of B. That means that, okay, you have three parts. You have total, right, which we have here. And then maybe x sum of A is equal to excess A. X sum of B is equal to excess B. A is ancestor B. I guess this is always going to be true, so we can put it here. But it's just that I need to draw it again almost. So A is ancestor of B. So that means that the three components are B or XB, XA mod XB to get rid of, and I say mod, I meant XOR. The reason why I guess I didn't talk about this during the diagram, but the reason is because you can think of this XOR as subtraction, right? That's basically the idea. Maybe that if I had explained that earlier, it would be more clear. But yeah, because you have the A at the root and then XA minus XB, but the minus in this case is XOR, right? I think, I mean, it's a little bit late in the video for me to mention this, I suppose, but I think if you were to do it again, think about it in terms of sum, right? If you just do a sum, then you could do addition and subtraction, and then once you understand that, you could do the XOR version of those sums, right? Sums and subtraction. And of course, minus is that, and you know, and then yeah, and then now, but if we're gonna write it out this way, maybe it's a little bit more understandable. Then now the third part, total minus XA, right? Yeah. So those are the three components, and of course this is an XOR minus. You can think of it that way because they both operate under the same spaces. Maybe I'm wrong with that one. I don't know what I'm talking about anymore. But anyway, yeah, those are the three components. So maybe we just write components. Components. But you can see that if you use the subtraction, it just becomes a lot more easier to kind of visualize it, right? And you even saw me struggling to be like, which one is which? And I'm like, oh wait, just think about it as a subtraction, and then now everything is easy to write. And then if B is A, then same thing, right? The components are going to be, okay, so XA, XB minus XA, and then total minus XB, right? And then this is just easy to write. Technically is this, but they're both the same, so that's actually interesting. I don't know. So I mean, it's stuff that when you see other people's code, you notice, and maybe they take some shortcut to combining these two together, and you're like, I don't understand this, and maybe stuff like that. You kind of come up, and then if they're not ancestors of each other, that means that they're and now you have XA, XB, and then you have total minus XA minus XB, right? So you have components is equal to XA, XB, total minus XA minus XB. And then now that you have the three components, yeah, you could sort them. And I'm just lazy, so I'm just going to sort them literally. And then the current delta is equal to components, the biggest element minus the smallest element. And then we just compare it to best. Best is equal to, is it min? Right? Yeah, min, best, delta, and then that's it. Okay, I think this is okay. Ooh, well, 9 doesn't seem, oh, because my best is 0, I'm just dumb. I set it to infinity. Got all the way to the finish line and then just messed up on the min. But at least that's like easy to see, right? Because it doesn't make zeros otherwise. I just didn't think about it. Yeah, and then that's basically it. Let's give it some min. I think if I wasn't if I was a little bit not lazy, I would just create an n squared case and then try to figure it out. But yeah, it looks pretty okay, right? So yeah, 1942-day streak, and that's it. How did I do last time? Wow, why was I so much slower last time? I got a wrong answer too. But yeah, the key thing is noting that I think the first key thing anyway is noting that n goes to up to 1,000, so you can do n squared stuff. That's the key part of the whole thing is that. And then just draw it out, visualize it out, visualize the tree. Once you see that, you can see the subtraction between the components and then draw it out in terms of XOR, right? I mean, and these three cases are pretty straightforward once you have the visualization. I mean, for me, you saw how fast it is once I had to write. And I didn't think I explained it correctly, but not precisely in a way, right? Because once I was able to be like, oh yeah, just think about subtraction, then these comes more natural. Versus trying to figure out like what component, and then you have to figure out what to XOR. It's a little bit trickier. And that's it. And this is this is just saying about adjacency list. This is the it ends as the this is n square, by the way, right? Because for each node we loop over the ancestor, so that's n square, right? This is linear though, but it's still dominated by here, of course. Yeah, and the reason why I was, and this is ancestor, n square for ancestor, and you can do an n log n algorithm for this lookup, and an log n for, n log n for processing and a log n for lookup, which is possible, right? But the reason why I didn't is because, well, the way that we do this is going to be n squared anyway, right? This is n squared, obviously. And then here you can kind of think about all these, this is all of 1-ish. I mean, it is all of 1. I mean, you could say this is 3 log 3, which is not a big deal. And you could even write it, you know, something like this, if you run, I think that's actually technically still more slower, but I don't know. All right, let's see if it is slower. I'm just curious now. But yeah, but that's it. Oh yeah, so you can see it's a bit slower. Max and min are kind of if they're not expensive, but expensive when you call them a million times, and now you're joining them 2 million extra things, which isn't a waste. So, but in any case, yeah, n square, and this is just try every pair, right? And this is just doing the math. I mean, the math is just visualization, so it's not so bad. But yeah, that is all I have for this one. Let me know what you think. Let me review what did I do last time? I mean, it seems like I did the same thing last time. Oh, I mean, this is Ancestor, but in a more funky way. So what did I do wrong? What? Maybe I did this stuff wrong. I don't know. Actually, I'm curious what I did wrong. 6 expected 11. I wish there's like a diff thing, because I clearly fixed it, so it must have been something silly. But I don't know. I mean, it's fine. It's the same idea as today, right? Yeah, that is all I have with this one. Let me know what you think. Thanks for watching, and yeah, stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.